Okay, start from this week, we are going to talk about machine learning. And we'll begin in this lecture with Scikit-learn. Scikit-learn is one of the most popular machine learning library in Python. The notebooks that is used in this lecture, you can find them in our class repo. I have rearranged the folders, the order of the folders, so that match the order in this semester. So the machine learning becomes the 04 machine learning. So you can find all of these Jupyter notebooks in this folder. We have already covered the first one, 01 from NumPy to MNIST. So in week 3, we cover the notebook 01, the number one notebook in machine learning folder, as an example of using NumPy to do things. So the task in that notebook is to do the classification for MNIST dataset. So recall that the MNIST dataset is a dataset for recognized handwritten digits. The first notebook, we didn't use anything about the Scikit-learn. We only use NumPy, and we use a very simple algorithm. That is the nearest neighbor. Very straightforward, naive algorithm. Although we do cover a little bit about how to speed up the algorithm so that we can do the inference in a reasonable time for a whole data set, for a whole training or whole testing data set, so that we can see the accuracy of the algorithm. And we actually find out the accuracy for this simple algorithm on MNIST dataset is about 97%. In fact, it is a little bit above 97%. So 97% is not a very, it's not too shabby, because you only get it wrong less than 3 times out of 100 times. Considering we are only using a very simple algorithm, the nearest neighbor. So what can we expect for more advanced techniques like machine learning or other techniques in Scikit-learn? So we'll start with the overview of what Scikit-learn is. And one of the highlights is that we are going to use another simple algorithm, that is linear regression. And we are going to apply this linear regression algorithm to MNIST dataset, and we are going to achieve 98% plus accuracy. To be noted that linear regression algorithm is for the problem called a type of problem called regression, which is different than the problem that we will mention about the MNIST. That is a type of problem we call the classification. Classification and regression are two typical but different type of machine learning problems. So you may heard that you should not and you cannot use linear regression to solve MNIST, or you should not use the mean square error loss when you're training a classification, when you're training a classification model. We're going to show you why this is true and why this is not entirely true because we can use linear regression to achieve MNIST for a 98 plus accuracy. So for the classification problem, the simplest, one of the simplest algorithm is logistic regression. Although the name suggests it is a regression algorithm, in fact, logistic regression is an algorithm for the classification problem. However, if you apply the logistic regression algorithm directly, naively on the MNIST dataset, you'll only get something like 90–91% accuracy, which is lower than our baseline nearest neighbor method we mentioned in week 3, and also, in fact, lower than the wrong method, that is a linear regression method, which we can eventually achieve 98% plus accuracy. Of course, if you apply it correctly, you can get it a better score comparable to the linear regression accuracy that we get 98% plus. And depends on the path of this lecture. Hopefully, we will reach to the support vector machine and about the kernel of the support vector machine. But because we have a lot of content in this week, so maybe we will not go into that far. Support vector machine is another algorithm for machine learning, typically for both classification and the regression method. We are only to cover the part of classification. And as an example, we are showing how to apply SVM to the MNIST problem, and it can actually get 98% accuracy at ease. So let's begin with the overview of Scikit-learn. To learn Scikit-learn is sort of like learning other libraries we mentioned before, like pandas, matplotlib, or numpy. The learning process is sort of similar because all of them are huge libraries. They contain tons of functionalities. So you should get an overview at the beginning and do not expect to understand all the functionalities available in this library. A good method is learn by example, and when you need something, try to look through the gallery and get familiar with the functionality of Scikit-learn. You do not have to go into a detail. You don't have to go in the detail of knowing how to actually run this algorithm. Just have an idea what's available in Scikit-learn. And when you need some functionality, you just check the gallery or documentation and to find out how to do that. The Scikit-learn provide a very complete library of examples. So just by following the examples, it can solve tons of different problems that you may encounter. In the official website, it categorizes the functionality of Scikit-learn into several categories, and these categories are also the main subfield of machine learning. So first one is classification. Like what we did for the just like what we did for the MNIST dataset. The classification problem is that by given some examples, we try to categorize them into different classes. Like for digital recognition, we separate them into like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different categories. And usually these categories are kind of arbitrary or discrete in typical situation. Like, for example, if we want to classify things into like dog, cat, or into cars, or bikes, or trucks, or boat, airplanes, they just like different sort of things. To emphasize the difference between classification and the regressions, let's talk about regression. Regression is another type of machine learning problem. And also, there are some similarity with the regression problem and the classification problem, and there are also some differences. The similar part is that it is also taken some input and try to do some inference about these samples. The difference is the output of regression is usually some continuous target. So there's not just 1 or 2, 3, 4 or some finite set of categories that are maybe just disjoint or discrete. They are probably just some, the output of regression is probably some numbers, real numbers or some factors. So for example, if we want to categorize the weather of the day into like a sunny day, rainy day, cloudy day, this is classification. But if we want to just to predict or to inference the temperature, like the highest temperature, median temperature, or lowest temperature of a day, then that is regression. Because temperature is a number, you can have like 25 degrees, 26 degrees, 25.5 degrees. It is a continuous number. However, although we can probably give some probabilities like 70% sunny, 30% rainy, something like that. A sunny day, a rainy day, a cloudy day is just different categories. There are nothing in between. There are gray areas, but it's very difficult to actually quantize the situations. So we generally consider them as different situations. Another type is like you predict the result of a sports game, like a baseball game, basketball game, or like a swimming, or like a sprint race. So for the classification, the result is kind of like who is in the first place, who win the game, who lost the game, or they tie. Or like in like swimming or like sprinting, running, since you probably get the result like predict who is the first place, who is the second place, who is the third place. Those type of things are for classification. But if you are going to predict the final score, like in a basketball, maybe it's 90 vs 85, the score is sort of continuous thing. In mathematical speaking, they are discrete because they are integers, they are discrete. But they are still numbers. So if you are predicting things like, you can actually do the prediction, say 95.3 or 95.2. Although the actual score is an integer like 93, 94, or 97. So, but even if you predict something like a fraction number like 95.3, we can still check how far or how close is your prediction. Like 95.3, the difference between 95.3 and 95 is 0.3. So that's pretty close. At least it's closer than like say 94.1, because the difference between 95 and 94.1 is 0.9, which is larger than 0.3. So that's what I mean by continuous things. So for those kind of prediction, we are saying this type of problem as regression. So that's the fundamental differences between the classification and the regression. We're going to go these topics, going back to these topics just a bit later, because we are going to discuss how to apply linear regression on classification problem, why and why not you should do that. And also, beside the classification and the regression, there are much more different type of problems in machine learning. For one thing is the dimensionality reduction. One of the most popular way of doing, an easy way, simple way of doing that is PCA. And the other one is feature selections. And also other things. We are not cover this topic this week, but we hope we are going to do that in next week. Also, there are a thing called the clustering. It's kind of like classification. It's just we don't have the actually ground truth or the actual label of things, and sometimes we don't even know how many classes we should need to class. But if you don't understand what it is, you don't need to worry it right now. We'll go back to it. Also go back to this in the next few weeks. Another typical type of problem is model selection. So how to select the best model for the problem. Which model should we use? We're going to cover this a little bit in today's lecture to select some models for best model for classifications. And also, pre-processing is something that you frequently do in machine learning tasks. It's kind of accompanying with other problems, because when you do some pre-processing, it may help you to solve the problem easier. We definitely will do some pre-processing along our way to solve the MNIST problem with linear regression, logistic regression, and the supervised machines. Like pandas and the matplotlib and the numpy, the Scikit-learn also has a very good documentation. The one documentation that I recommend is the user guide. It serves as a purpose of a practical guide for machine learning, because a lot of you might more interested into deep learning or maybe in large language model, and do not have maybe you do not have patience to learn deeply in the sort of traditional or classical machine learning materials. However, the techniques in the classical machine learning is still very important, and it many times is useful for you. one way to learn them quickly in a more practical aspect is to just read this user guide. You are probably going to walk through a lot or most frequently used machine learning techniques. And this guide is pretty complete. Although some of the methods that is not implemented in Scikit-learn, like you might want to use like XGBoost, LightBoost, CatBoost, or those kind of boost things. They didn't cover them, of course, but there are similar things in Scikit-learn. In Scikit-learn, there are gradient boost. So although they are not exactly the same, you get the idea and some fundamental, just get some fundamental knowledge about, background knowledge about all of the topics. So Scikit-learn has been integrate a lot of different libraries into the Scikit-learn itself as a backend. So it already covers a very wide range of tasks in machine learning. So by just following or just read through this user guide, that is very helpful. Another way of reading this practical guide, like user guide of Scikit-learn, is try to read the index. Try to see the left side. There's a navigation part. You can see each chapter and each sections. So for the topics you are interested in, just go to the corresponding chapter or sections, and you can find a lot of different things. And look around the topics you are interested in. You will find probably you were overlooked about some topics that is useful for your problem. It's just you didn't know that. So this one is a very good guide for machine learning. It does not replace the theoretical part and a full semester and 4 lectures for all the machine learnings. But if you want to learn machine learning and get ideas, it is a very quick way to familiar with topics in machine learning. Okay, so let's begin the topics that we're going to cover in this week. The linear regression first. And you can find the notebook in our class repo. The primary notebook for linear regression is 02 linear regression IPY and B. So what is linear regression? This one is taken from the Wikipedia. So one terminology is ordinary least square. Basically, it's just saying we are using a linear formula as our model, and we try to find out the weight or parameters such that minimize the least square error. So you can see this formula. If you are familiar with formula, this one is a simple formula. We get a data of x and y. X is considered as input, and y is the target. So when we train the method, we get a training data set, a training samples. So in the training samples, we have x and y pairs. You can see that x is in capital because we are considering the features in multi-dimensional features. So not just only one feature. In the diagram you see right here, it mostly illustrates for the problem with only one feature on the x-axis. But in real world or in a lot of interesting problems, things are going to be more interesting when we are consider the X to be multi-dimensional. But for visualization, it is easier to understand. We only consider one-dimensional feature. So in this case, the X is just the X-axis, and we get some Y's here. The Y is the data that we collect. We want to train the algorithm. That is a ground truth. And you can see the blue line here is our model. Because we are consider our model is never ever truly correct or exactly the same as the real world. It never has been, or it's very difficult to be so. So no matter you are consider the modeling or the theories in physics or chemistry or in biology or in a lot of different scientific fields, almost all models are not entirely correct. Like Newton physics, they are just approximate of things. And even with the Einstein's relativity theories, it's just a model. We are not 100%, or we probably are pretty sure they are not exactly what work is going to be happen in the real world. But some of the models are useful. So in this case, you just don't worry about that the blue line is 100% perfectly aligned with the black dots, because we are just using a simple model to see how close our prediction is going to be. And usually we are modeling the differences as a noise. They are sometimes assumed to be follow some random distribution like Gaussian distributions. However, we also apply these linear models on real world, and of course the noise may not follow the distribution, ideal distribution like a Gaussian distribution or the distribution we know, but still they are still useful. Okay, so let's go back to the modeling, but just keep in mind we don't have to do the prediction 100% perfect. So we get the X as input and the Y as output, a target output. And try to find a model that's as close as the data as possible. And this model is linear. The W is also a metric. So we are doing the metric multiplications of X and the W together. The X is determined by the dataset collected for training, and also Y is also fixed because we already determined the training data. The only thing that we can optimize, you can see here, is the W, which is the weight. So this one is the model. We try to find the best matrix so that can minimize the square error. So we are calling this the ordinary least squares. So this is just for one-dimensional Y output. Okay, so that is just for the definition and the basic theoretical part. We're going to, when we go to the Jupyter Notebook, and as our class title suggests, we are mostly for the practical things like software and tools. If you look into the notebook, you will see that in the first cell there is a strange thing right here. We use from Scikit-learn. Scikit-learn means Scikit-learn. But there's an EX after the Scikit-learn. EX probably stands for extension or extended. We import a patch Scikit-learn. This one is from a package called the Intel extension of Scikit-learn. So we from Scikit-learn imported this patch Scikit-learn and run this function. We probably almost have done nothing right here. You just see after you run this cell, you only see this information. This one is only for accelerations. If you are using an Intel CPU, by running this line, it will hack or patch the whole Scikit-learn library to make it run much faster. In some cases, it will introduce instability because some algorithm is going to be crashed or failed running if you apply this thing. But for the majority cases, at least for our use case in our class, it is going to be speed up the algorithm like 2 or 3 fold if you are running on an Intel CPU. So I'm always running this one at the beginning of our notebook. If you are not running on an Intel CPU like you are running on maybe on a Mac or maybe on other ARM machine, then this one does not help or maybe not even able to run. Or in some case, you are using an Intel CPU, but in an older platform, it is not supported, and you kind of find trouble when you running the rest of the notebook. You can just skip this cell and disable it. So let's go to construct our example dataset right here. We're trying to construct a simple example dataset of only one-dimensional feature, X, and one-dimensional output. This is our construction. Our X is just random uniform between -10 and 10, just some random X. And our Y is mostly in proportion, linear proportion to X. So I use X to times these hidden parameters. This parameter is supposed to be hidden, that we don't know. And by using machine learning algorithm, in this case the linear regression, we are trying to figure out these hidden parameters. However, because this one is just toy examples, we actually know the true answer here. We choose one like 1.72 to make it sort of difficult to guess. Okay, so we control our dataset by using X times hidden parameters, and to make it seem more interesting or a little bit more realistic, we add some noise right here. We're using standard normal distribution noise. So the final dataset constructed is like this graph. It falls on close to a straight line, but not exactly. You can change the noise level by adjusting the 1 to be another number, or you can also change the hidden parameter to another number as well, to repeat the experiment and give you an idea of how good and how plausible the linear regression can do and should do. Before we are going to using the Scikit-learn, we are going to use NumPy functionality to do the least square, so that you can compare and to see why you should use Scikit-learn. And maybe you are going to get the contradictory or the different opinion, maybe, but I give you the choice to see the difference so that you can compare the result. In fact, you can use NumPy functionality to do the least square or to do the linear regression right here. In NumPy, the linear algebra submodules contains a function called the least square. So if you give it the x and the y, it will compute the least square to do the minimization, to do the optimization for you, and to find out the hidden parameter. So this one is the code, and the hidden parameter it found is 1.706959293, which is not correct because our correct answer is 1.72, but it's very close. You may change the noise level to see what kind of noise level, or maybe you can change the sample, the size of sample. Like we are having 50 samples right here. If you are going to get like 500 samples, the error is going to be much smaller. So you can play around with it to see how good and how bad it is. And what is the things you can expect it from running the linear regression algorithm. This is something you are going to expect if you have this kind of noise level. You cannot have 1.7, like 19999, this kind of things. You do not expect the result to get that close because you only have 50 samples and you have this kind of level of noise. This is something you can only expect you can get. That's the best things you can expect. There's some theory behind it, but you can play around with it so that you don't have some unrealistic expectations. Sometimes people are trying to do things that is impossible because they're trying to use like very little samples to achieve a very high accuracy. Even with these ideal examples, we already know the formula behind it is in fact a linear thing. Sometimes you don't even have this perfect modeling. We already have a perfect modeling, but with this level of noise and this many samples, this things is that you can expect it. In a real world problem, you probably don't even have the correct modeling, and you still get as little samples, and you get as much noise level like here, and if you are expecting to get a higher accuracy, that is impossible. There's some theory. If you are interested, you can go to study the theory. The linear regression, those kind of things, is extensively studied in previous literatures. So you can find a lot of results regarding to the least square or to the linear regressions. So let's plot it to see how good is our prediction. The red ones are predictions, and the blue ones are the actually data that we generated. We're using the same X, and you can see that there are some differences, but they are pretty close. And of course, you can observe that all the red dots are lying on a straight line, perfectly on a straight line. So by seeing and the visualization, the prediction and the data, you can get an idea of how good is your prediction. Although we didn't get the hidden parameter 100% correct, this is our prediction, and you can see it is a reasonable prediction. Even with the perfect like 1.72. You can try to plot the prediction with the perfect parameters. You probably will see that by the visualization, you probably prefer the rate prediction here. This is because, I mean, we introduce the noise. So by the noise that we have on this data, the rate one is probably the best fit. I mean, it in some sense it is the best fit because we already run the optimization. Okay, so seeing these pictures, you get the idea of why it cannot guess the correct answer. It is because the noise we introduced and the limited sample we provided. There's no way the model can guess the correct ones because this one fit even better than the correct ones. However, one reason you might think that we should use Scikit-learn instead of the NumPy functions we just mentioned is because usually when we do a linear regression, we are not only consider y equals to ax, we consider something like y equals to ax plus b. So recall that we only modeling things like x times 1.72. But in general, we are consider a linear modeling, mostly for a linear function like a affine transformation things. So it is something more like y equals to ax plus b, not just y equals to ax. However, by using some transformation, typical tricks, this is not a problem. We can still solve this type of equations or modelings by using this, like the NumPy function least square. It is because the bias is not a problem. The constant is not a problem. We simply consider a multi-dimensional feature. It's just the second dimension is always 1. You can see that our original x is the x, and our second input feature is always 1. So we are not seeing ax plus b, we are seeing ax plus b times 1. So by viewing this way, we can formulate this problem into a problem that the least square function can solve. Okay, so we are just going to introduce it to be a 2-dimensional input. The output is still the same, it's still the y. And by optimize this a and b, ab is w, this ab are w. This is our modeling, and we are optimizing this modeling by minimize the difference between y and this x1 doing the dot product with AB. We can do that. So that is not an issue. However, why should we use Scikit-learn? Before we answer the question, let's see how we do the linear regression with Scikit-learn. So this is how we do it with Scikit-learn. First of all, we have to import the linear model submodule here. And we use linear model dot linear regression things to construct a regressor. That we call the, because we call something a classifier, then we call this a regressor. So this is a object. First, we construct object. We're not just calling a function. We're constructing an object that is considered to be the model itself, and it can do certain things. So it is an object called the linear regression object. It is a regressor, or it is a regressor. So that's the first thing, not too difficult. And secondly, of course, we construct our data first. Sometimes you need to load it from the learning training dataset or that you collected. But currently, we just create a toy example that from kind of theoretical modeling here. So just note that our x is something around 0 and has a size of 50. And our parameter should be 3 and 4. So the correct answer should be 3 times x plus 4 equals to y. But we also add some noise right here with the same size. So how do we use the Scikit-learn to do the linear regression? Easy. We call the regressor that we just constructed and use a method of it called the fit. Of course, we have to let the fit method know what is the x here and what is the y. So after you do the fit, it learns everything you need. So for the linear regression in particular, we can use these two things to find out the parameters. So first one is the answer is 3 and we get 3.07. And the second one should be 4. It has a name called the intercept. And correct answer is 4 and we get things pretty close, 3.997. So that's how we use it. And when we want to do the prediction, we can usually always call the predict. I didn't put the code right here. I probably should, but you can see the result right here and here. You just call the predict. So one way to think that it is even more complicated. Instead of learning just one method, you have to learn like 3 methods. One is to construct the regressor, and secondly, you have to call the fit, and you also need to. It doesn't return the result directly, but you have to see a document to find out the parameter, and you have to learn another method to predict the result. This is the prediction, and we apply it to the whole range of like from -10 to 10, and to see kind of see the ideal result of the model that we just train and get the parameter and see the ideal result of the model here to compare it. So you can see it is a perfect line, and these blue dots are the data. So one thing that is good about Scikit-learn is it has the pattern. Of course, it has 3 things you need to learn and a little bit more about each models, like parameters, or how do you get the learning parameters, or how to control it. But the good thing is it has a fixed pattern. There are 3 things you need to learn, but these 3 things is for every task of machine learning, every different backend, every different algorithm. You only need to learn these 3 things. First, you declare or construct sometimes the regressor and sometimes the classifier. You just construct the object, the algorithm object. Here, you declare and construct, and later you fit the algorithm with the data. And after this is done, the training is done, and you can use the predict to use the model you just trained to do the prediction. So everything is follow this pattern. So that's the benefit of using Scikit-learn. If you want to change the linear regression to, say, SVM regression, or maybe for a neural network, you can only change the declaration part. The rest of the code are mostly the same, or probably exactly the same. You don't need to worry about anything. Like you probably can do something like benchmarking metric, do the metric to see a result. To maybe you generate the report. Everything remains the same. All you need to change is a declaration. You change to another algorithm. Maybe you change some parameters, hyperparameters of it. Or maybe you change some backends to see if it runs faster. But all you need to change is the declaration part. So that's the pattern of Scikit-learn. And because of this pattern is popular and a lot of people knows how to familiar with this pattern, a lot of library actually mimic this pattern, mimic the Scikit-learn pattern, which they call the Scikit-learn API things. So after you're familiar with it, a lot of library is in your disposal. You can use it without change a lot of different things. And if the libraries are in quality, they are written in quality and produced in quality, there should be no surprise. I mean, it depends on the implementations. So if you follow this pattern, you should get no surprise. This applies to the quality things applies to the libraries or functionalities in the Scikit-learn libraries, of course, because it is a quality, and also applied it is a quality libraries, and also applied to some of the famous libraries. So if you follow this pattern, if familiar with this pattern, you will get this surprise. This is a really good thing and very convenient things to do. The drawback is that sometimes things cannot fit into this pattern. It's not suitable for this pattern, or in some cases they can, but it makes things a little bit awkward or a little bit more complicated. But I think these patterns actually works and benefit a lot of people. That's why these patterns are popular and Scikit-learn library is popular. But again, as I mentioned before, you can have a different opinion. I'm just present the things so that you can decide. Another thing is Scikit-learn has a ecosystem and functionalities built around of this pattern. So for example, we can easily use Scikit-learn to get the dataset, some simple dataset that we can play with and play around with and do some preliminary experiments. And they are ready for use with Scikit-learn patterns, the Scikit-learn pattern. So let's try to explore one of the sample dataset. So you can run from Scikit-learn to import dataset, and let's load the diabetes dataset. In Jupyter Notebook, you can use the question mark before or after a method or function to get documentation. So by running the question mark here, you'll get a very long. Let me check to the notebook, which I have already presented. So because that is difficult to show on the later, close. Okay, this is difficult to show on the slides, but you can see it right here. It has a full documentation of what is inside the dataset. To do a full description, like the labels and what it is. And we also do some, I believe low diabetes. You can see the data itself in here. So it has the data part. It is a dictionary, and it has a data part and a target part. So one way to actually look inside the dataset is to use the SciPy. There's states. SciPy states it can describe the dataset, kind of like what we do for pandas to describe the dataset. So you can see the minima, maxima, like the mean, median, or maybe other like skewness, standard deviation, things like that. Or you can just use the pandas. So we're using the pandas to explore the data. Like we say, you can install the data frame viewer. What we use is in the Visual Studio Code, there's a data frame viewer. You can actually to play around and look through the dataset. I'm giving you a simple code right here in the notebook to put labels to transform the data in the Scikit-learn into a data frames form. So you can see the labels right here. And also, I'm also putting a target right here. The goal is pretty much that we are trying to use the age 6, BMI, BP, S1, S2, S3, S4, S5, and S6 to predict the target. I believe there's this is related to probably some values related to diabetes, like how serious the diabetes is, or you probably can read the document. It will say what the target is. I forget what it is, but that is the things that we are going to predict. So that is something the linear regression or regression in general can do. We take some input and output value, try to predict a value that is a real number. It is not a category like a dog, cat. You probably want to output a probability of how likely it is a dog or how likely it is a cat. But it is just a number. The goal is to output it as close as possible. Okay, so first of all, let's load the data so that we can use them in the training data set. Let me first shuffle it. It is usually a good idea to shuffle your data before you feed them into the training things, because sometimes the order is not random. Even though the order is random, it doesn't hurt it to shuffle it. So I always shuffle the data before I use them. Otherwise, you can use them directly, because the X, what you need to fit into the fit things, you simply use the data part as your X and the target part as your Y. The only reason I need to do some shuffle to do something is because I want to shuffle it. And by shuffling it, I can split it into training data and testing data to verify my result. Okay, before I do the full linear regression, let me do it one by one feature. I have a cell in the notebook that you can try to do it interactively. By interactive, I mean you need to modify the code. So you can change the feature and to see the first one, the second one, and third one to see what happens if we only use one features to predict the result. The cell is just right here. So you simply change features index and you get a different result. It will also print the feature's name, so you can see what the label it is. So the second one is sex, because mostly just male and female. So you can see the X is either on the far left side or on the far right side. it seems that this vector alone does not does not have much power of prediction, because the red line is the ground truth. The blue line is the ground truth. The blue dots are ground truths, and they seem very similar, no matter what x is, and the average, the mean of them are pretty similar. These are other variables, other features. It looks like this feature, the third feature, seems to be a little bit meaningful. This one is too flat, so it seems that this vector alone does not affect the result too much. So maybe this one and this one are, if we can only choose one feature, I probably will choose this one. And if we can only choose like two features, in this case, I probably will choose this one and this one. Okay, so after we play around with it a little bit, and we probably will get some result for this one feature, and we'll get a loss. This loss can serve as a baseline, because when we do the full input, especially if you are not familiar with, you probably will do it incorrectly or making some mistakes. So suppose you are already familiar with one linear regression with one feature, one-dimensional feature, then you probably will doing it correctly. Or even if you do it incorrectly, because you can easily visualize the whole things, you will figure out what's going wrong. So you probably will get some result. Then we will see what happened when we're using all the features. Then you will get a training loss and testing loss. If your training loss is higher than the training loss of this guy, you are probably doing something wrong. And if the training loss of this guy is very similar to this guy, there are two possibilities. One is that you are doing something wrong. The other thing is the other feature does not help much. That is also possible. But we kind of limited them into, if it is much better than this guy, then it is probably, we are probably doing something right. So we are less worried about where we were making some mistakes. But by doing the simple thing first, you are going to reduce the chance that you were going to make mistakes. So in some cases, you even get something like stupidly or hugely, insanely huge loss right here, even in the training. It happens, believe me, it happens. Sometimes it happens. So that you can easily find out what was the mistakes or what went wrong. So always do the simple things that you can visualize first. But how do we actually visualize the result when we use a multi-dimensional feature? We still want to visualize it. We are not giving up the visualization. We still want to visualize it. So one way to do that is you just use one feature at a time. We're still using one feature as x-axis, and one. Of course, you need the y-axis as the target. But we are trying to see the same graph, but we just limit to one features at a time. This is sort of like a dimensional reduction, but in fact it is. It just, we only pick one of the dimension at a time. So this is still useful sometimes, but we also have other methods to do the visualization. This one, the red line is just a diagonal line, independent to the model. it is y equal to x. It is a line of the equation y equal to x. The reason we need to have this line is to compare our result. So because this graph, for this graph, the x-axis is the prediction, your prediction, and the y-axis is the actual value. It's actual value. So if the prediction is perfect, everything is going to be lie on the red line here. If everything is very close to the red line, then we are doing a good job. So now you can see that the prediction, so for example, this guy means the actual value is like 75, and our prediction is maybe 180. So this prediction is definitely off. But it serves as a pretty good example to explain what this graph means. So for this one is also the same. The prediction is like 70 and the actual value is 200. But all other values are, this one are pretty spot on because they are very close to the red line. And overall, they seem to have the pretty good trend, like from left bottom to the upper right, bottom left to the upper right. Also, the blue spots are for testing data, and the green spots are for training data. The reason that I put the blue spot larger and the green spot smaller is because we have more training data. In this case, I'm using more training data and less testing data. So if they have the same size, the blue spots will or test things were going to be unfairly less represented. So by making them larger, you can see them much easier. And of course, another reason is we are more interested in the training performance than we are more interested in the testing performance than the training performance. So I make it a little bit larger than the necessary for the reason that I mentioned before. From this graph, we can see that our prediction is pretty okay. The model is kind of weak. So even for the training data, they didn't perform that well. But by comparing the performance on training data and test data, they are similar. They are not overfitting, like we are going to discuss in detail later. But the performance on the testing data is not worse than the performance on the training data. So that's a good thing. So we can see on this graph. So the prediction is something, not very good, but it is something. Another way to do the visualization is using box plot, because sometimes we probably want to see how good is our prediction. Like maybe if we predict it to be 90, what is the range of actual value? So if our predict is 270, do we need to worry about it or not? Also, if the prediction is 30, in most cases, it's probably under 100. But in some cases, at least for our testing data, it is at most like 120. So we can use this plot to make sure what happens. And by using the mean right here, you can see it is perfectly at least for the mean or the median, it is very positively correlated. So that's another good thing. The thing that we need to worry about is the range right here. For the middle prediction value, it is still very likely that it can be to reach a very dangerous level. So that's the not good part of our model, the part that our model doesn't perform very well. But that is expected because we are only using a very simple model and we didn't try to do things with it, apply more advanced technique with it. And we are not going to do so because we are mostly focusing on MNIST dataset. We are trying to do that later. It is still worth doing. I mean, you can still, if you are interested, you can still try to apply some techniques on it. But currently, we are not doing, in this notebook, we are just serving it to explain the mechanism or the functionalities of the Scikit-learn. We're not, and the visualization right here. We're not trying to do a good job or to try to solve this problem right here. We're using another example. Another concept that is occur often in the machine learning area is the concept of overfitting. So what is overfitting? We are using this simple example to explain the result. Our ground truth is 5 times x plus 3 plus some error. The error is some Gaussian noise. So this is our data. We are trying to fit it with various different models. If we are fitting it with a linear model, it will seem like this one. We can also fit it with a quadratic model. That is, our model is like ax squared plus bx plus c, something like a quadratic polynomial. And we want to determine the parameters a, b, c. And similarly, we can fit it with a polynomial of degree 5. And we can also fit it with a polynomial with degree 20. Because we only have like about 20 data points. So we can actually fit perfectly on our data set by using a polynomial that with higher, with a degree high enough. In this case, 19 is probably enough, but I'm using a 20 degree polynomial. So the loss, you can see the loss is 0. We can fit it perfectly. However, this one may not be a good idea. So the training loss become 0. It may not be a good thing. Although you can see that the linear model has highest loss, and the quadratic has the second highest loss, and the degree 5 has less loss than quadratic 1, and of course the degree 20 have the perfect loss, which is just 0. However, because our model, recall that our model is in fact this one, we are just generally a very limited sample to train our model. The real problem, and task we need to mimic is this 5 times x plus 3. So if we are having this loss to become training loss to be 0, at the test time, it is not good, because you can see that when we generate another set of data right here, then the prediction is not good. If we are using the linear prediction, the loss is comparable to this one. You can see this 14.84. This is 14.72. They are roughly the same, almost the same. But for the degree 20 polynomial, you can see that this is the polynomial here. The loss for the new data is going to be like more than 1000. So this is definitely what we want. This phenomenon is a typical overfitting phenomenon because we are fitting the data too well with a model that is too complicated. We can always do that with complicated enough model. We can always fit our data perfectly. But the data is just a sample, not the problem itself. So if you fit the sample too perfectly, more often than not, it will not fit the problem that we intend to solve. So this is the situation. So how do we avoid this thing? Because we only get the training data, right? So how do we know? I mean, the degree 20 is tried very hard to solve the problem. We actually get a perfect score, and all we get is the training data. How do we avoid this? Are you asking us to not optimize our parameters, hyperparameters, or not trying to work hard, not trying to get the best score? The thing is, we have keep in mind our challenge is something more random. So we keep that in mind. We have some techniques help us to avoid things like this one. But keep in mind, a lot of these ideas have some assumption, and some of them, for some of the techniques, the assumption is not that clear. It's sort of like a heuristic. We are not going to that detail, but keep in mind, this method is not a theory that has been proved. At least you have to have some assumption. But in the real world case, in most of the time, we don't have a very explicit and clear assumption. So a lot of things are heuristic. So one way to do that is regularization. The motivation of it is we'll show in these formulas. But before that, let's see one popular regularization that is called the L1 regularization. So instead of just optimizing our goal, we add some challenge here. The alpha is some hyperparameter you need to determine beforehand, like 0.1 or 1. We need to determine. We will go to the model selection to handle how to pick this alpha. But the thing is, in addition to optimize our target, our loss function, we also want to get a penalty when the weight has a very large L1 norm. So combine these two together, our actual optimization target becomes this one. So why do we want to have penalty when the L1 norm of omega is too large? Before I explain what the L1 norm is, you just think about this one. L1 norm is a norm. A norm is kind of a measure of the size of things, like the length of a vector. That is L2 norm. Sometimes we use L2 norm instead of L1. But L1 norm is just the taxi cab distance. That is another kind of distance. But that is a distance if you consider a vector. So this sort of regularization is tried to, or at least it attempt or intend to do, is to get rid of the case of the first one. So suppose our function, we have a data, and after the fitting process, we get two models. The first model is this guy. And the second model is this guy. The first model is like 3,129 times x power to the 5 and 1,314 x power to the 4th. And similar like I didn't write it completely, but you can see this one is a very complicated formula. And the number, the parameters, coefficients of this polynomial is huge, or like thousands, or even tens of thousands, 100,000. It's a huge parameters. And the other one is like 7 times 5 power to 5 and minus 3 times x plus 1. This one is simple. So suppose they performs similarly on the training data. So which one is supposed to be a better model? I mean, if we want to predict for the, new testing data, we probably will guess the second one. So if this one is the case, you can see that this coefficient are smaller, much smaller than this one. This coefficient are more widely, very wide, very large and wild. So to avoid these things, we give some penalties for the coefficient that too strange, too kind of large or too big. So that's why we give this L1 penalty, because the L1 norm of this parameter is probably just like 7 plus 3 plus 1, which is just 11. And the L1 norm of this parameter, it will be like 3,000 something plus 1,000 something plus 600,000 something and plus 9,000 something. It is huge. So the penalty will be very huge for the first one and will be relatively small for the second one. So that's the idea behind regularization. But instead of using L1 norm, we can use other norm as well. Although L1 norm is more compared to L2 norm, well, more benefit for the sparse coefficient. There are some differences. We are not going to detail, but there are some reasons we choose L1 norm a little bit more often than L2 norm. But sometimes we choose them both. And in some cases, we choose other kinds of norms. Maybe other P norms. The definition of P norms right here. So you're probably familiar with L2 norm and probably see the L1 norm, knowing this is just the summation of the absolute values. But they have a pattern. So in general, we can define the P norm, LP norm, which is just the absolute value of each component to the power P, and we sum them together and get a P's root of the summation. So that's called the LP norm. If you substitute the P by 2, you will get a L2 norm. If you substitute the P by 1, you'll get a L1 norm. The P can be something like 0.5 or 1.5, or can be the infinity. By using infinity, it will become, you take a limitation, it will become the maximum norm. We just pick the maximum element of all the components, the maximum absolute value of the component. So it becomes the maximum norm. So that's the common notations. But for the regularization, we probably mostly use the L1 norm and L2 norm. So if you are using the L1 norm as a regularizer on the linear model, we call the model to be Lasso. So the Lasso model is simply the linear regression with L1 regularization with L1 regularization. If you are using L2 regularization, we're calling is a rich model. So that's unnecessarily complicated, right? It's simply just a linear model with L2 regularization. And the other one is simply L1 model. I mean, linear model is L1 regularization. But the thing is, people use familiar with this name, and they are shorter. It is easier to pronounce to say lasso or rich than say linear model with L1 regularization. It's not that much shorter, but it's shorter, and it is the thing, the word. Currently, the thing it is, the fact you should have to accept. So why not just use it? Also, the lasso is simply linear regression with L1 regularizer, and the rich is the rich model as L2 regularization. And if you want to use both L1 and L2 together, it is called an elastic net. Okay, I know there's no reason, no pattern at all, but it's just called an elastic net for historical reason. So just you can use the name. I think it's perfectly fine if you say that I use linear regression with L1 and L2 regularizer. That's totally fine. But you can also say the elastic net. So for example, we can use the linear model.lasso and specify the alpha to be 0.2, and we can use the same fit, use the Scikit-learn pattern here, and to do the training. And we can see that our square error here is like 3000, like here. The test error is still a little bit, test loss is still, test error is still a bit larger than the training error. So you can choose a different value of alpha in order to make the overfitting problem, to reduce the overfitting problem. But sometimes some alpha, a bigger alpha, may reduce. If you choose the alpha to be big enough, it will definitely reduce the overfitting problem. But the thing is, the training performance is going to be reduced, and perhaps you get an even worse testing performance. It just, if you get a very, very big alpha, the performance between the training and the testing is going to be negligible. But you have to have some balance between the overfitting and the testing performance and the training performance to get a better testing performance. So how do we choose the right alpha? You probably think it's simple, it's easy. We just run through all the different alpha and to see which one has the best test performance. But the thing is, you cannot do that. You should not do that. Do not choose alpha based on the testing results, because if you do so, you are practically overfitting the alpha on the testing data. You're kind of wasting the testing data because you are optimize the alpha on the testing data. So that gives some risk of overfitting. So because we are practically optimizing alpha on the testing data. So that is essentially fitting the alpha on the testing data. And the testing data is not supposed to do anything. You should not do optimization against the testing data. So that is usually not a good idea. Sometimes you actually do that, but you know that you shouldn't do that. It's just you don't have any choice. and you know that the result is just a number that probably doesn't mean much, but it probably gives you a lower bound or upper bound things, but it doesn't reflect to the actual performance of the testing result. So the thing is, we construct another data set that is independent to the testing data. That we call the validation data. So that's why we sometimes, when we get the training data, we split the training data into two parts. A part is called the validation data, and the other part is called the actually training data. That's sometimes we do that because we want to do something that is like model selection or something independent to the regular training process, but we still need to adjust or to optimize some parameters. Then we do that on the validation. So for example, when we want to do the early stopping, that is another way to prevent overfitting. Or we want to do the model selection that we are going to do right now, that we can use validation to do so. There are different ways to do validation. A common way is to split the training data into two parts. So we keep like 10%, 20%, or maybe 50% of them to be the validation data. The other way to do that is called the cross-validation. This is an umbrella term. A lot of different ways to do the cross-validation. Probably the most common way to do that is called the K-fold cross-validation. That is what we do illustrate right here. So we do the things in different iterations or different batches. We pick like in this case, you just think we have a 4-fold cross-validation. So we put like 25% of data as our validation data, and the other 75% as our training data. So we do our process and see the testing performance as our validation performance. And secondly, we pick another 25% of data as our testing data, and the rest of 75% as our training data. And we do it over again and to see a result. And we do repeat this process the third time and the fourth time, so that every element has a chance to being a testing data, and also being like three chances to being the training data. So in this case, there are two benefits comparing to just picking one validation set. So one is that it is more fair, because sometimes when we pick the validation data, we're just getting lucky or unlucky. So the validation data is not that representative. It is maybe performance too good or too poor. It happens a lot because sometimes we are dealing with the case that something is very rare but important. So in these situations, there are a lot of probabilities that we can choose a very bad validation data. So in this case, it becomes more fair. In another benefit is that sometimes your training data is just like you have only 10 samples in your training data. If you just pick 2 of them as your validation, or even 5 of them as your validations, it is very difficult to do. I mean, the precision of your benchmark is not very good because your validation data only has 3 samples. The result is, if you are doing the accuracy, the result is either 0/3, 1/3, that is 30%, or 2/3, like little more like 70%, or 3/3, like 100%. That's the whole space of possibility, potential result you can get. You only get 4 potential outcome. So if your goal is to have like above 85%, the only chance you get qualified is to get it 100% right. Sometimes it is too difficult. So if you are doing cross validation, your validation have like 3, 3, 3, 3. At least you get 12 samples, so you can have a more precision on your testing matrix. Also, that's another benefit for doing cross validation. The drawback of a cross validation is, of course, you have to do things many times, and it may be very time consuming. So depending on your situation, cross validation is one of your tools, but it's not like other tools. It does not always work. Okay, we are going to use the validation, cross k-fold validation, to select the alpha. Because instead of using testing data, because we cannot use testing data to select alpha, we use the fake testing data, that is the validation, to do the similar things. We're trying to find out the best alpha so that the validation result is the best. This seems to be reasonable, although it may not always work, because sometimes you have the best alpha for the validation data, even for the cross validation, but the alpha may be performs poorly when you have the new test data. It happens in some cases. So there are always different cases. There's no one method can solve. There's no silver bullet can solve any problem. You have to understand the assumption or the hypothesis. Sometimes you don't even have that. You have to have some guesses of what is actually happened. But right now, let's focus on the process of using cross-validation data to find out our alpha. In Scikit-learn, a submodule called the model selection, it can help you to compute the cross-validation score. So it can like automatically do all the things for you. So that's another benefit of using Scikit-learn, because if everything is built around the Scikit-learn pattern, there's a lot of tools available to use. So one of the tools is here, the cross-validation score. If you have any object that satisfy the regressor API in Scikit-learn, you can just call this function, and it will do all the process for you automatically. So what is the score if we want to do the regression for, let's say, the least square loss or like a mean square error? One score is called the R-square score. It is very common for regression tasks, especially for the linear regression algorithm. So it is a score to see how good your model is. This is a formula. The basic idea is to compare the basic model, the baseline model, and your model. So this is the square error of your model. Your prediction is Fy, and the ground truth, the actual value, is Yi. So we compute the square error. It's called the SS residue value. Okay, of course we need this one, but we also need another one. It's called the it is called the total something, TOT something, but I like to call it the baseline. It is a baseline error. You can see what is our baseline. Our baseline is simply the average of the testing data. The average of the testing data. That is y bar. Of course, this is a little bit not the same. It's not exactly the same as the baseline, because we are using the testing data to determine the y bar, the mean of the y. But the thing is, the average, the mean of the data is quite stable, quite robust in most of the situations. If you are taking the mean of the training data, it will be very close to the mean of the testing data. It is actually governed by the law of large number. Unless you have a very ill-posed problem or very malicious problem, that is what we are going to. Sometimes we are going to face in real world, because a lot of time you are getting training data from one distribution and getting the testing data from a totally different distribution. This happens in a real world problem, because people usually don't know what they are going to work with, and when you collaborate with people and do the real world job, there are always some restriction and limitation. So that happens. But aside from that, if you are taking things from the same distribution, by the law of large number, if your training data, you have enough training data, the mean of the training data, mean of the target of the training data should be the same or very close to the mean of the target of testing data. So although this one is used by is using the testing data, the mean of the testing data, it doesn't matter that much. So roughly they are just a baseline. Okay, so the idea is comparing this fancy advanced your model with some baseline estimations. So the estimation is just, we simply predict the result by using the average of the result to see what the error. So if you are doing a very good job, so this should be much less than this guy. So this fraction, this ratio should be very little. Ideally, it's very close to 0. So your R-squared score is very close to 1. 1 is the best score you can get for R-squared score. So what is the lower bound? What is the minimum? If you are if your model performs as bad, as poor as the baseline, the ratio of this guy becomes to be 1. So 1 minus 1 equals to 0. So 0 means in general a very, very bad or like the worst score. But the fact is you can perform worse than baseline. Sometimes maybe you're doing something wrong, or maybe for other reasons it is not converge or something else. But sometimes theoretically you can perform much worse than it. So in fact, it could be negative infinity. It could be negative infinity, because if your loss is so large that is, like 100 or 10,000 times the baseline large, then this one can be arbitrarily large. So 1 minus an arbitrarily large number can be negative infinity, can approach negative infinity. But in general, usually we are consider R-squared to be between 0 and 1. and 1 to be the good score, the best score, and 0 to be, in general, the worst score. So if I do occasionally see people getting a negative R² score times 2 times. So just be aware, if you are getting a negative score, means you're probably doing something totally wrong. You are worse than just output a constant, and that constant is the best constant available, but you are only output a constant number. So that's the R², which is used by default when we do the cross validation for linear regression. Okay, so when we want to select the alpha, we given a huge choice. We use a log space between -4 and 0, and we test these 50 different alpha to see what happens. For each alpha, we run the cross validation and get a score. So in this graph, the red line is the mean of the validation score, and we have a arrow band right here. This indicates the 1 standard deviation. So this is the red line plus 1 standard deviation, and the bottom dashed blue line is the mean minus 1 standard deviation. Because when you run the validation, cross validation, K4 cross validation, you got a lot of validation score. So you can have a mean, you can have a standard deviation. But this is a graph that we get. So you can see the score, because the score is larger, the better. So probably something around here should be the best one. Probably something around here is the best one. You can choose the mean, the largest guy for a mean, or maybe you can, to be safe, and to assume the worst case, you can choose the largest one minus 1 standard deviation. The mean minus 1 standard deviation, and choose the largest one. Okay, so in this case, we can use the lasso plus CV and give it an alpha space. It will use the validation to find out the best alpha using the validation as a reference, as a target, and it will find out the best alpha. And then you use the best alpha to train your lasso on the whole training data set. You can also use the small, you have a K4 cross validation, so you must have K different models. You can work with these models and combine a new model. There's ways to do that, which you can do something like an ensemble, or you simply average them, the model weight. In this case, because this is a linear regression, you can also do that. But the thing is, another way to do that is after you get the alpha, you simply use this alpha as your parameter and try to use this alpha to train your model and test it on test data. So in this case, we get a validation score like 0.4, which is still okay, which is okay. I'm not trying to optimize the method to achieve the best result. I'm just demonstrate how you can use this method. The topics I want to cover most primarily discuss is the thing that can we use linear regression to do the classification, because there are a lot of misconceptions about this topic, and some of them are just entirely wrong. So I'm using this MNIST as an example. Although MNIST is a dataset that is kind of too easy, so in the real world dataset, you may encounter a different phenomena. But the example I'm going to show right here is still indicate some result that you may think give you some doubt at the fact that people usually assume too fast. Okay, so let me show you the example. So first of all, I'm going to show you why linear regression is not suitable, it's not good for doing classification. Before we can show that it is not good for doing classification, it has to be able to do the classification, at least in some sense. So it is in fact can do the classification. If in principle it cannot, you cannot find a way to allow the linear regression to do the classification, there's no discussion, because there's no good or bad, no good way or poor way. Or I mean, you cannot discuss is it good to use it or it is not good to use it. The thing is you cannot use it. But the fact is you can actually use linear regression to do the classification. It is just not suitable to do that. But how do we actually do the classification using linear regression? One way to do that is we simply fit the data. So suppose we have a very simple example right here. We have two classes of object. One is positive number. One class is positive number. The other is negative number. So we have two classes, positive number or negative numbers. 0 can be discarded or ignored because it's just one case. Or you can treat it as a positive number. But because it's just one number, we don't really care about. So we only have positive number or negative number. This example is so easy because when you give a number, that number is the feature. We simply compare it with 0. We know it is positive or negative. So it is a very, very simple example. But we are just trying to do it with to classify it with a linear regressor. So how do we do that? So for each positive number, because we only know it is, the label only knows it is a positive one or negative one. So although we know much more because we know what number is and how to actually classify, we know it is easy, but we pretend it to be a regular classification problem when we don't know much about the detail. So what we receive is X is a number and whether it is positive and negative. So we can give any positive a label like 1 and give any negative label as 0 or negative 1. So for the sake of convenience, simplicity, we give the positive labeling number to assign it a label like 1. All negative, we give a label like negative 1. So the graph looks like this cross, like these crosses. Then we use linear regression to actually fit this data. So just to imagine that we can actually apply this method to any classification problems, because we can assign label like 1, negative 1 or other labels. If we are considering the binary classification problem, we can always do that, and we can apply linear regression. And we will get a linear regression model result. Okay, so at the end, how do we decide the prediction by using this model? We use the output. If the output is greater than 0, when we output it is a positive number. If the output is less than 0, then we output it as a negative number. So you may ask, at this point, you may ask, if we already know how to compare 0 and the number, why don't we just simply compare the number and with 0 and the input with 0 and get a perfect prediction? I mean, this is just an example of showing we can. If you really feel uncomfortable with this example, we can use a very complicated example. But I'm just using a simple example to illustrate the situation. We can actually use a two-dimensional or many. If it is a one-dimensional problem, it is either very difficult to or impossible to use a linear thing, or it is a higher dimensional problem, which is very difficult to illustrate it. So I'm using this just to illustrate the example. You imagine it is going to be a more complicated examples. Okay, so by this way, we can actually do the classification, and in fact, this method is very reasonable. The only problem is the result is not very good, especially if the dataset is imbalanced. If the dataset is kind of balanced, like 50% the data in the data is positive and the 50% is in the negative, you can try that. In fact, most of the time, this linear regression method actually works pretty well. The only reason, if you have enough data and 50% of them are negative and 50% of them are positive, the linear regression actually works. The times it doesn't work is, in this example, is that it's the case that we have imbalanced data. In this case, we have more positive data than the negative data. So you will see that because this straight line want to fit into this kind of things, and because you can see that we only have the value, type value to be 1 or -1. So if we have a lot of large positive number, the error is going to be very, very big, because this straight line is going to be quite larger than the 1. So if this one is going to be missed or a little bit, if we move this guy to a little bit right, then the loss will increase a lot. So if we have more positive data, the decision boundary is the 0. The output is greater than 0 or less than 0. If we have imbalanced data, the decision boundary will be more close to a -1. If we have a very imbalanced data, this decision boundary will be very way off to a very left one. So, but this is kind of by chance. So sometimes it is way off, sometimes it is more close to 0. But this situation is more serious when we have imbalanced data. If you are using the balanced data, this is very difficult to observe this phenomena. But the first reason we don't use linear regression is because the loss is not very sensible. It's not very reasonable. We have too huge loss even if we are guessing it correctly. Okay, but anyway, that is kind of a theoretical and a simple example. Let's just try to classify MNIST. Let's just try to classify MNIST. What will happen? Recall that we use the nearest neighbor and the class neighbor method and use NumPy to do the classification on the MNIST data. And just for a reminder, this is the MNIST data. We are feeding the model of a picture, 28 by 28, handwritten digits, and try to get a result. We in the training data and in the testing data, we have the actual result like 7210. And this is actually a predict, but because the prediction is pretty correct and accuracy pretty high, so there's no difference. At least in the first 20 numbers, there's no difference than the actual number. But this gives you an idea what the dataset is. And in a nearest neighbor method, we actually get a 97% accuracy. So let's try the linear regression here. We simply put the y as it is, like 0, 1, 2, 3, 4, 5. And we put the x, the whole 28 by 28 as a factor, as our input. And we do the linear regression. So the result will be something like 6.34, 2.29, 1.62, or 7.89, things like this one. They are not integer, but we probably can pick the closest integer. So for example, this should be 6, and this should be 2, and this should be 2, and this one should be 8, 5, and 6. And to see what happens. So you see, the accuracy is kind of like, first, there's no overfitting. The training accuracy is like 23%, 23.6%, and the testing accuracy is like 23%. This is better than the average, like the random guessing. Because if you guess it randomly, you will get something like 10%. So is 20% a win or a achievement? That is always the question we want to ask. So that's why we need a baseline. And we actually have a baseline, the nearest neighbor. The baseline gives us a 97%. So 23% is pretty bad. I mean, really, really bad. If you get something like 70%, 85%, that is poor result. Or maybe like 92%, it is still no good. But 23% is really bad. So can we improve it? So one way to do that is to do the one-hot encoding. Because the reason that the regression itself does not work is because their target space is different. One is continuous. Like 0, if we want to predict the weather, the temperature, like 22, if our prediction is 22 and the actual result is 23, then we are doing something. But if we are treating it as like a categorical classification, 22 and 23 are totally different. One of the example is right here. Our first prediction is 6.34. The actual result is 7. In fact, it is kind of close, but it is not close enough. 6.3 is not good at all. It is as bad as 1.2, as bad as 1.5, or maybe 100. But in the regression case, 6.34 is much better than like 1.5 or 100. This is not. So we have to do some modification on the target space to make it more reflect the fact of the correctness. So one way to do that is do the one-hot encoding. So what is one-hot encoding? Because every digit is not the numerical meaning of it. It's just a category. So we are using a factor to represent each category. This factor has a length of 10. We use 1, 0, 0, 0, 0, 0 to represent the first category, and 0, 1, 0, 0, 0, 0, 0 to represent the second one. And of course, 0, 0, 1, 0, 0, 0 to represent the third one. and so on. So we can use a simple fancy indexing to transform the number like 50419 to the one-hot encoding. So if this is our target and we are output things like this one, this makes much more sense if we want to apply regression on the target. It is still regression. It's just we have a more sensible target or reasonable target. Because 0, 1, 2, 3 is not a continuous. They are not lying on the same space. They are different category. So we are kind of using the one-hot encoding to make them discrete. As the, this encoding is more reasonable. And of course, and this one is more like the toy example the positive and negative number things we are using, because the positive and negative things is more like it is positive or not, and by this factor we are saying it is category 1 or not, it is category 2 or not, and this one is definitely the 1, 2, 3, 4, 5, 6, the sixth category, which is number 5, because we start from 0. So this is in fact more close to the example we presented before. In fact, Scikit-learn has a utility function called the one-hot encoder. So this one is reside into the preprocessing submodule. So this is kind of things for doing the preprocessing. Okay, well, we are run out of time. You can also use this one, and you can see that it also fit the Scikit-learn pattern. You construct the object, you fit the data, and transform it. This is not predict because we only need to transform it. So after doing this, we get a accuracy of 86%, which is still pretty bad. At least it is not overfitting, but it is still pretty bad because, it is much better than the random guess, which is 10%, and much better than the way that we did before, like 23%, because that is incorrect way. We're doing it more in a more correct way to do that, to give it a more fair evaluation to do that. But you can see that it doesn't perform that well. It is reasonable well, 86%, but it is still far behind the nearest neighbor. However, you can see that the testing accuracy is not far, actually it's better than the training accuracy. And the training accuracy is very poor. It's far behind the nearest neighbor method is far behind the baseline. So it is mostly because the model capacity, the model itself is not representative enough. It is not expressive enough to model the data. We need to do something to make the model more capable, more expressible, so that at least we can increase the training accuracy. There are many ways to do that. One way to do that is feature engineering. Because linear data is very limited data. It only can do because you can see that is a very simple model. It is a linear model. So if you use it directly, only a very limited type of questions can be useful. The method can be useful for only very limited number, very limited type of questions problem. So usually when we use linear regression, we are doing some feature engineering. So for example, remember the overfitting example we mentioned before, here. not only we can do it linearly, or we can also do it quadratically or in a higher dimension polynomial. All of these higher dimensional polynomial fitting can be done using linear regression, because we can take like x squared or x cubed as a feature. We are not limited to x itself. We can use the polynomial feature of this x. So if we are using polynomial features, we can make the model more expressive, because like this one is more capable to fitting in a more curvature, more curved curve. So that's what we are going to do. And in fact, we are going to use a very simple and easy feature engineering way to do that. We are going to use random features. Not only we are going to use some like sometimes when we say feature engineering, we are choosing some handcraft features. Like, okay, if we are doing a digital digits recognition, we probably get the curvature of each point, or like is here like the gradients things, or like different direction of gradients. People use those kind of visual for like digit or image recognitions. There are some things to do similar things. But right now, we are doing something really, really simple. We're trying some random features. So how do we do that? First, we construct a random uniform matrix. The values of this each component in this matrix is either uniformly between -1 and 1. And we are going to map, using this matrix to map the features of the image of the digits, handwritten digits, which is considered as a vector of the length of 784. We are mapping it to like much more features. I'm using a rather large, you can even use a larger one, but I'm using this like 16,000 features. But all these features are randomly generated. So I simply multiply this training data and map this 800 features into 16,000 features. And I have to add some non-linearity inside it. Otherwise, it is just linear regression. So I'm applying absolute value. You can use like a sigmoid function, hyperbolic tangent, or like rerule or something else. But right now I'm just choosing a really kind of obvious and harmless nonlinearity function, like the absolute value. So I'm just choosing one. Not every nonlinear function works. They still make difference, but a lot of function works. So this choice is quite arbitrary. You can consider it's quite arbitrary. Arbitrary, but works. So every time we have a random feature generator, so every time the result should be slightly different. But if you are using a size that large, the result will be very consistent. You can use a small value like 4,000, 5,000 if you don't have that much memory, or if your computer is running slow, take too long time to do so. You can use a smaller size to repeat my experience. 4,000 works, but you probably get something like 96 or 97% accuracy. But in this case, if you are doing something like what I did right here, exactly the same, you probably will get something close to 98%, which beats the baseline, our baseline already. And we are only using the linear regression. Okay, I'm using the NP argmax to pick our prediction is just a bunch of vectors, like 10 numbers. in a factor. So which output should we pick? We pick the largest one because they are 0, 0, 1, 0, 0 something. The most recent or easy choice is choose the large prediction because it seems to be more confident on that component to be positive. We either have a 0 or positive. In idea, we have a 0 or 1. 1 is positive and 0 is 0 non-positive. And so in this case, we just pick the largest output. So I use np.argmax to choose the largest class. I mean the class that has largest output. And the accuracy is like this one. We get 98%. So linear regression can do the classification. At least for MNIST, it can do very well. One thing that this works that well is also because our data is very balanced. Each digits, I mean, the digits are evenly split into different categories, like 0, 1, 2, 3 to 10 to 9. So let's explain a little bit of why this one works okay. I'm not saying this is perfect because you can get something like 99.9% if you are using some SOTA method to do that. But this is relatively okay results and running quite easily to run this kind of thing. Can we improve this? Still improve this? Yes, we can. So another way to do that is to use the logistic regression. I think probably today we are going to only cover the logistic regression. So the support family machine will be covered in next week. That is more reasonable way to do that. So I'm going to talk about the logistic regression. Okay, so recovery issue is because the shape of this model, like a straight line, is very different than the step function. I mean, the blue dots more looks like a step function. They are so different. So we probably should use another shape of things that is more close to the step function. We're using logistic function. So instead of we can still using a least square, although we are going to use another loss function. But that is not the crucial part of things. The crucial part is our model, output model, is kind of like a straight line. We want our output to be more like this one, so that the difference of a large number, if we are guessing it correctly, the loss is not going to be arbitrarily large. So for this function, although if we are guessing correctly, there still be some loss, some error, but the error is going to be mostly small. At least they are bounded, the loss is bounded. So that's the idea of logistic function. So you can use the click this to a Wikipedia page to see the things. So basically we are still using linear regression, but before we output the result, we feed our output to the logistic function. So our output is going to be bounded between 0 and 1. If we are using a hyperbolic tangent, which is very similar to the sigmoid, or we scale the sigmoid a little bit, then the output can be between -1 and 1, which is more suitable for our plot right here. So anyway, if we modified our output a little bit, we can still do pretty much the same thing. But in fact, in logistic regression, we are using a negative log or like cross entropy loss, which is different than the mean square error. So technically, it is a totally different algorithm. But the idea, I mean, logistic regression does improve a little bit, but the part is not contributed by the cross entropy or log part. It's mostly contributed by the different shape of the output. So we still use the linear regression, but before we output the y, we feed the y into the logistic function and to modify the shape and to compute the loss. So here is an example. The red thing is the original linear regression. You can see that the shape is different. The decision boundary is off. However, for the if we are using the logistic regression, the decision boundary is very close to 0 and more stable. You can run the notebook and run this one a lot of different times. You can really see the stableness, robustness of the logistic function. And most of the time it will between the smallest positive one and the largest negative one. So although it's still a little bit off, the difference is mostly because we don't have enough data. Because in principle, we still, so suppose your smallest positive number is 0.1 and the largest negative is like negative 0.5. There's no guarantee the boundary should be 0. It could be anything between negative 0.5 and positive 0.1. Could be anything between there. And it depends on your data. It's probably more likely to be something like negative 0.3 or 0.2, right? Because in the middle of both of them. So this boundary is close enough, in my opinion. We are testing this data on the iris flower dataset, which is also you can use directly in the Scikit-learn dataset submodule. In this dataset, we have 3 different kinds of iris flower, and we get 4 different features, like the length or the wideness of these flowers, and to use these features to classify which category this flower is. So by using logistic regression, you can see that fundamentally it is a binary classifier. So if we only pick 2 of them, 2 of the category, we can easily do the classification. But you can see that the decision boundary is still a straight line. So in this case in particular, if we are not doing the feature engineering, this is impossible to classify them perfectly, because there's no one straight line can separate the red dots from the purple dots. But you can see that the result is pretty good. It's pretty good. It can also do the multi-class. There are many different ways to do that. You can do it using like the neural network softmax method, which is called the multinomial method in the Scikit-learn here. So this one is a multi-class classification boundary. You can see it right here. We are choosing just 2 different features. Okay, I have to explain this graph. We choose 2 different features and use this graph to visualize the classification. Suppose we choose 2 features like the first one, the second one. The x-axis is corresponding to the first feature and the y-axis is corresponding to the second feature. Because the output y is kind of discrete, like we said, when we're doing a plot, the most precious resource you have is the x dimension and the y dimension. And since you only have 2 different categories, if you are using this on the y dimension, y-axis, it's kind of waste of the resource. And also, because the category is not continuous, there's no structure, it makes less sense to put them on an axis because axis is a continuous thing. So for visualize the category classification problem, we usually don't put the Y on any of the axes. So we have two axes for the feature. We use the color or the shape of the dot to represent the different class. So that is what this is about. If we have 3 different classes, we can use this one to see our decision boundary and the result if we are using these 2 features. Okay, since we are going into the more serious into the classification, we should not use the method to compute the accuracy like using NumPy and get the output and compute them directly. Although they still useful because you can still touch the data and see what it actually happens. But by using Scikit-learn utility functions in the submodule matrix, you can do the matrix to see the benchmark, to see the result much more easy. Much easier to see the result, much easier. For example, first we get a prediction. And if we want to have the accuracy score, we simply call the matrix.accuracy score and give it Y and Y prediction, and it will return the accuracy score. And also, because this is a multi-category classification, we are more interested in a thing called the confusion matrix, because the accuracy alone may not showing all the truths about the performance of the model. Sometimes if you want to debug the model to find out what we can improve of the model, the accuracy score itself is not enough, especially for the case that the dataset is imbalanced. So we have a more detailed things we call the confusion matrix. In the confusion matrix, these columns, these rows are for the actually results for each sample, and for the columns, we are for the predict results. So for the first class, this means it is actually a setosa, and our prediction is correct. And in here, it reads that our setosa, for every setosa images, our prediction is 100% correct. And for every our prediction setosa, it is 100% correct to be the setosa. And for the case of first color, out of 50 samples, 48 of them get correct, and 2 of them is getting to be misidentified as the Virginica. And for the Virginica case, 50 of the samples, out of 50 samples, 46 get correct, and 4 of them get misidentified as versicolor. And on the other hand, for a prediction, for given image, and we get a prediction as a versicolors, we get 52 results, and 48 of them are correct, 4 of them are incorrect. And similar happens to the Virginica predictions. So that's how we read the confusion matrix. A popular way of showing confusion matrix is using this graph, especially if we have a lot of different classes, like 100 different classes. We use the brightness of the color to indicate a number, so we don't need to read the number. However, for a case that just have 3 different cases, 3 different classes, I think the table view is more easier to read and get precise results. But you can still get a very a quick glance to see the result is pretty good, because all the dark things intense is on the diagonal axis. So it seems to be pretty well, and you can identify this one is slightly darker. So this one are two false result. So by consider each class, we can actually generate a more human result that is more suitable for human intuitions. By the way, we are using a function called the classification report, also available in Scikit-learn. There are also more functions available in the submodule or matrix, but we cannot actually introduce all of them. I'm just using this one as an example. There are more on our notebook, a little bit more on our notebooks. Okay, so one way to interpret the data is using the precision, the recall, and maybe F1 score. So how do we do that? We usually consider a class at one time. When we consider the Setosa class, we consider it as a positive class. So you can call it the class or the category, or maybe you just call it a positive category. Each class will have its turn. So at the first step, we consider it as positive, and the second iteration, we consider this one's the first C color as positive, and the third one, Virginica, as positive, but one positive at a time. When we consider Setosa as positive, let's check the confusion matrix right here. If something is positive, I mean, in this case, Setosa, it is actually Setosa. It is positive. We call it positive. And if it is not Setosa, we call it negative, because they are not Setosa. So every color, every first C color and every Virginica images are negative samples, and every Setosa images are positive samples. And our prediction, we also have positive prediction and negative prediction. If our prediction is Setosa, then it is a positive prediction, and otherwise they are negative predictions. If our prediction is positive and it is in fact positive, then it is, we call it true positive. True means we predict correctly, and positive because both of them are positive. If it is actually negative and our prediction is negative, then of course we call it a true negative, because our prediction is negative and it is correct. So it's called a true negative. Okay, so because we have correct things called true, the incorrect things we call the false. There are also false positive and false negative. If we predict it positive, but it is in fact negative, if like in this case, but we got a 0 right here. If we predict it is Setosa, so we predict it positive, and suppose it is in fact first C color or Virginica, or anything not Setosa, then our prediction is wrong. We call this guy false positive. And similarly, if our prediction is negative, but it is in fact positive, then this is false negative. This is false negative. So it is very easy to remember, right? If they are correct, they are true. True positive, true negative. if they are incorrect, it's a little bit complicated, but I mean, the actual ground truths cannot be false because they are truths. They cannot be false. The false things only apply, or the true and the false things only make sense to apply to the prediction. So the false positive means your prediction is positive, but it is wrong. And the false negative means your prediction is negative and your prediction is wrong. Okay, so false negative always means your prediction is negative, and the false positive always means your prediction is positive. So what is precision? Precision means how accurate is your prediction. So among all the positive predictions, how many of them are correct? How many of them are correct? So for example, the precision of setosa is 100%, and the precision of the versicolor is 48 over 52, and the precision of Virginica flower is 46 over 48. So you can see our calculation right here. The precision is 100%, 92, and 96. And another related concept is called the recall. Recall means in this category, in the actual category, how many of them have been identified correctly. So in this case, setosa, we have 50 pictures of setosa. All of them are correct. In the versicolor, we also have 50 pictures, 50 images. Only 48 of them are identified correctly. And in the Virginica case, 56 out of the 50 images are identified correctly to be Virginica. So that is the recall 46 over 50, which is 92%. So this is precision and the recall. There are also something like recall is also called the true positive rate, TPR, because the TPR or TNR, true negative rate, always take consider the actually negative and positive case. So the TPR is equivalent to the recall. They are also called the FPR and the FNR, false negative rate and the false positive rate. And so what is the F1 score? The F1 score is some kind of average between the precision and the recall. I think is geometric. Not geometric. You can check the definitions. I forget the terminology. But this is I think it's harmonic average of F1 of precision and recall. So it is always between the precision and the recall. So that's a quick way to check calculation of the metric, because sometimes if you can see that F1 score is not in the range between 92 and 96, then they are computed incorrectly. And if the precision and the recall are pretty close, then F1 score will be pretty close to the arithmetic average, the mean of precision and recall. The support means how many samples in this class, the actual class. In this case, all of them are 50, 50, 50. So what are the macro average and weighted average? Macro average means that we average all of these things out of, we in this case we have like a A1 over B1 and A2 over B2 and A3 over B3. The macro average is A1 plus A2 plus A3 over B1 plus B2 plus B3. That's called the macro average. But the weighted average is just the average of these three numbers. Because we have a balanced data, so these two is going to be the same. And also, because if you consider it carefully, what is B1 here? B1 is 50. No. What is B1 plus B2 plus B3? B1 is all the every samples that is predicted as setosa, and every sample that predict as versicolor, and every sample that predict as virginica. Then you can see that the total number of B1 plus B2 plus B3 is 150. It is the same for the case of recall, because the recall, although we count it differently, we count all images. We count the first one is 50 because we have 50 images in setosa. B2, in this case, the B2 is versicolor and the B3 is virginica. So it is still 150. So also, what is A1, A2, and A3? A1 is the true positive of setosa. A2 is true positive for versicolor, and A3 is virginica, true positive for virginica. And in fact, they are the same here. The A1 here is the true positive for setosa. True positive. This one, A1 is A2 is a true positive for versicolor, and so on. So you will see the macro average of this guy and this guy is typically the same, unless you have some unidentified case. Otherwise, they are the same. They are always the same. So macro average of precision and the macro average of recall are usually the same. There are many metrics because a lot of different areas use similar ideas but use different terminology, like in medical, in biological, in physics, in statistics, and in a lot of different areas, or in social science. Sometimes they use sensitivities, specificities, or precision or recall. A lot of them are pretty much the same thing. You can check the graph in Wikipedia. They have a very good graph to actually explain the definition of all these things, and have a table to list all of this terminology, like what is true positive, for example, what is false negative. This is, we predict it to be negative, and we predict it to be negative here, and the actual positive things. So we underestimation. These are also other terminology to describe the situation of false negative. And also, we also call the false positive as false alarm, overestimate, and this one is hit, and this one is correct rejection. In different area they have different terminology. You have to be quite careful and observative, because people are so familiar and they don't even kind of understand what the definition is. But you can always translate every meanings back to this table. And also there are something like TPR. Let me choose the recall things here. Where is our recall? Okay, this one is TPR. sometimes we call the sensitivities. This one is called the FPR and TNR. You can see a lot of differencing. Okay, and also it has some related things like accuracy, F1 score, to see other concept about that is also considered as a matrix for classification, multicast or binary classifications. Another thing that we use a lot is the RC curve, which in the x-axis is false positive rate, and on the y-axis is true positive rate, TPR. This shows the trade-off between the false positive rate and the true positive rate. And sometimes we calculate the area below this curve as a metric of how good this model is. The larger is the better. A similar graph is called a precision recall. We have precision here and the recall here. And this graph shows the trade-off between the precision and the recall. Okay, finally, we can also apply the logistic regression on MNIST if we are using the multinomial way to do the multicast classification. If we do it directly, it can be done pretty quick. You can run it in like 23 seconds. However, the accuracy is not so good. You get the accuracy like 94% in training and 92.5% in testing. So typically you are going to only get like 92 or 91% if you are using logistic regression. Depends on your actual implementations. You are going no more than 93%. If we look at it directly, it seems to be okay because it's over 90 seems to be fine. Less than 1 incorrect out of 10 attempts. Much higher than 10%. But because we know the baseline and we are doing it sort of using the wrong way by using the linear regression, we know we should achieve something like 97% or 98%. At least 98%, because logistic regression is supposed to be better than the linear regression. So what did we do right for linear regression? The one thing is we changed the outcome space to be like 1 hot, but this one has already been done here for the logistic regression. This one has already been done. So the only thing left we should do is for the feature engineering. We can use different features. One way to use is use polynomial features. So Scikit-learn preprocessing provide the functionality of polynomial feature to generate polynomial feature. I use a toy dataset to demonstrate what it does. The toy dataset had 2 features and 1, 2, 3, 4 samples. If you consider first one as X and the second one as Y, don't be confused with the target. We have 2 features, X and Y, suppose. Just forget about the target. So what is polynomial feature? So first one is the constant. The second one is X itself, and the third one is Y itself. And because we are using degree 2, we are consider all the polynomial generated by X and Y. So this is X squared, X times Y, and Y squared. Or you can verify it by computing all of them. So this one is 2 times 2, 2 squared is equal to 4. Or maybe this one's all 1, so everything is 1. And yeah, and everything else. What if we are using a polynomial feature? The first thing we observe is it is kind of impossible because we have too many features. Although polynomial feature is kind of intuitive and it sounds sort of elementary, and is possibly what we should do at the first step, But the fact is, their usage is sort of limited because if we are using degree 2 on our data, like we have already like almost 800 features. The degree 2 polynomial feature is going to have like 300,000 features. That's too much, or too many features. That's too many features. Because we are not only have x, y. For each pair of different features, we have a second order degree feature. So it's more like 800 times 600, 800 squared divided by 2 over 2. So it's a lot of features. This is going to be too large to be processed in short time. So instead, we first downsample the images. We're not finishing right there. We start want to use the polynomial feature, but we begin by downsampling the image to have less features and then apply the polynomial feature again. And of course, you can see that when we use polynomial feature, we're still using the declare, fit, and the prediction, in this case, transform pattern of the Scikit-learn. So in this case, we're downsizing the image to be from 28 by 28 to 14 by 14 and apply the polynomial feature. So in this time, we still get a lot, but it's only like 20,000 features. This is comparable to what we did for the linear regression. The number is still a little bit more, but around the same neighborhood. In this case, the accuracy we can get is 97.67, which is not great. It's okay. It's probably because of downsampling or because the polynomial feature is not that efficient. Because maybe they are too similar. Maybe they are too similar. So let's try the random feature again. So we're using a random feature. In this case, we only use 8,000 feature. You can try more, but it takes a little bit longer time. I'm choosing this one so it won't run too long and achieve reasonable accuracy. Because our goal is like 98%. We're not trying to make it so good like 99.9 or 90, at least 99%. We're just trying to demonstrate it kind of work can defeat the baseline. So if we are choosing this random feature, 8,000 random features, we still using ABS, we can get testing accuracy like comparable to the linear regression. Just comparable, not defeat them, just comparable. This is probably because if you are using more features like 16,000 features, just like what we did for linear regression, the accuracy won't increase too much. It is still like a little bit over 98% usually. So in this case, logistic regression does not beat the linear regression too much. It is probably because the MNIST dataset is so good that it's so balanced. So the benefit of logistic regression does not contribute too much accuracy. But in general, it's still easier because we can use only 8,000. It cannot be done with linear regression. If you are only like 8,000 random features for linear regression, it would be something like 97.67% accuracy. But in the logistic regression, we can use only 8,000 random features. It's just that if we are increasing the number of features, it doesn't help that much. Okay, so this is probably because we're working on a very good data set. So, okay, so we So in this case, linear regression is indeed a good choice, okay choice. I'm not saying it's great. It's okay choice for doing MNIST classification against what people usually say that you should not use linear regression to do classification. They are kind of true. They are right, but they don't know why it is right. In this case, if we are focusing on MNIST, all of the drawbacks of using linear regression, it's reduced to almost invisible. Okay, next week we are going to talk about SVM and to do some spoiler. We are also doing it in MNIST. It can be quite easy to achieve like 98% accuracy in very, very short time, which is a very powerful tool for doing classification and in some case doing regression. So see you next week.